Hub flanges are vulnerable to breaking and sometimes will. Stress risers can result in hubs cracking also. That's less common than rims, but it does happen. You see a couple here. And 3 more examples here. This kind of deformation of a hole in a hub flange can occur, often does occur, either above or below the hole as you're seeing it here, depending on the orientation of the spoke and the spoke head. This will occur gradually at the neck of the spoke as the aluminum in the hub flange accommodates itself to the large tension put on the spoke. It will cause the tension of the spoke to go down a little bit, but it's not a structural concern in the hub itself. Proper spoke length is critical, especially when using aluminum nipples. Now I'm going to give you a peek into one of the portions of the chapter later on about nipple and spoke threads, but just to point out something that is pertinent to this discussion here, I see in that picture that I have only about 4/5 of the threads are being used between the nipple and the spoke, and if the spoke has reached full tension at this point, it's adequate but not optimal for a brass nipple, but more importantly, it's too short for an aluminum nipple. The next few slides will show you what can happen with aluminum nipples if the spokes are too short. Here is a photo of a wheel where 2 of the heads of the nipples have snapped off. On the left we have a shaft. There's the end of the spoke, and there's the head of the nipple that snapped off, and over here is another case where the head of the nipple snapped off. Here is a reference spoke, and then the spoke under it where the end of the nipple has broken off, and in both cases the length of the spoke is the same. The spoke did not go nearly far enough into an aluminum nipple. And without the nipple being supported by the spoke going all the way through it, the end of the nipple is vulnerable to snapping off. Now, the point of this discussion, which obviously gets pretty nerdy, but details make a difference, is that you have to make sure that if you're going to use aluminum nipples in a wheel, the spoke has to be long enough to avoid the head of the nipple snapping off. Here's another example. This is a ZIP 404 Firecrest rim, and you can see that the nipple has broken off at the head. Proximate cause of this is a fundamental error coming from the factory in that ZIP used a spoke that was too short by about 2 millimeters. If we use this line here to represent the spoke bed, we can see that the spoke is pulling on the nipple, and therefore the nipple pulling on the rim at the point where the nipple is at its weakest, because the spoke is not reinforcing the nipple head by going all the way through. In this situation, the failure to observe a fundamental wheel building principle of using the correct spoke length resulted in a premature end to somebody's bicycle ride. If something breaks in a wheel, you want to go beyond just observing that it broke and replace it. You want to find out why it broke. And I have to tell you that it's really maddening to see so many wheels built incorrectly with the wrong length spoke in combination with an aluminum nipple, because it's easily avoidable and it's very time consuming and costly to repair. Damage to spokes can cause stress risers in places that they otherwise do not occur. Here's another example of where stress risers have developed that will create weaknesses in the spokes and cause premature braking. In this case, the damage occurred when the chain overshifted the largest cog on the inside of the cassette and went crashing down against the spokes. The spoke at the bottom became severely bent in the process. And a close-up of the other 2 spokes reveals that they have become gouged out somewhat because of the severe contact with the chain. If a chain goes past this point here and goes down inside between the largest cog of the cassette and the spokes, causing the aforementioned damage. It's almost always caused by either limit screws being incorrectly adjusted in combination with a bent derailleur hanger. Poor spoke angles can often cause premature breakage of spokes. In this bike here, which has 36 spokes, I will restrain myself and just say that I think that this wheel has room for improvement in its design. I think there's a future for these kinds of e-bikes or electric bikes, but there are some problems to work out first. And I'm going to walk you through this slowly with lots of graphics so that my point will be made with crystal clarity, I hope. So we start here with a rim and a hub. So this would be a rim and a hub if we were going to build a wheel for a regular bicycle. The dashed line in the hub shows us where the holes are, and the hole-to-hole diameter in many hubs is somewhere around 40 or so millimeters, 40, 50 millimeters, something like that. This is going to be a 36 spoke wheel, so here you see 18 holes in the hub flange. And here are 18 nipples in the rim, all ready to be connected via spokes to the flange. But my spoke is not going to be radially laced like I show there. It's going to be tangentially laced, and that's going to give me a 4-degree angle. This is a 26-inch wheel. I have a bead seat diameter here of 559 millimeters, and I measure a hole-to-hole flange diameter of 170 millimeters. This is our 170 millimeter hub with 18 holes. And that hub likewise has to be laced into the same rim we had before. If I lace my spoke into the hole on the hub that had the same position as the original one, I have this angle here, which is a monstrous 17 degrees. Well, what's been done to reduce that angle slightly is instead of lacing it into that hole there, it's laced into this one here, which makes it a little bit less tangential and reduces the angle down to 14 degrees, which is still pretty enormous. And then when I look at this wheel, I see, to me, what are obvious stress risers and the large kinks that are required in the spokes in order to make those angles. To see the consequences of this clearly, let's look at this nipple in cross-section and see how the threads of the nipple align with the threads of the spoke. Well, I actually have counted these. In the spoke, I have 19 threads, and in the nipple, I have 17 full threads and 2 half threads. This shows us the ideal situation of the spoke continuing to go exactly in the same direction as the nipple, but in fact there's always going to be a little bit of displacement one way or the other. A little bit is okay. This graphic shows a small displacement of the spoke from the straight line, and note that the spoke is not contacting the unthreaded portion of the shaft of the nipple. Here, however, I've got a bad situation because I've actually got now 2 bends. I've got a bend where the spoke comes out of the threads, and I've got another bend where the spoke has to bend itself against the end of the nipple. And that, my friends, is what you're seeing there on every single spoke. And it all grows out of the fact that the rim that is being used was not intended to be used with a hub with that big a flange. And the problem is sort of painted over here by just using spokes with a gigantic diameter in hopes that they won't break. A better solution would be a rim that is drilled specifically to be used with a large flange hub so that the angular problem we just saw is reduced. Perhaps a more elegant solution is this bike here, where the motor is near the bottom bracket and the rear wheel is more like a normal wheel. So far we've been talking about the picture on the left. Let's look at the picture on the right now, where the direction of hole drillings can help the articulation. This is a cross-section of a ZIP toroidal rim. The rim is 4 millimeters thick at this point that we refer to as the spoke bed. If the hole in the rim were drilled straight out, then the nipple would come straight out also. But if we look here, we don't want the holes to come straight out because we want the nipples to be pointed toward the target flanges. We want the spokes and spoke holes to be angled alternatively to the up flange and then the down flange. If I look at the rim from the inside, all these spoke holes appear about the same, that is, along the center line of the rim. But if I put these rods in, I can easily see the alternating nature of the angle with which the holes are drilled through the spoke bed. When I build my wheel, I just make sure that the spoke angles correspond to the flanges that the spoke is supposed to go to. Now, I think it's pretty obvious how the direction of the hole through the rim helps the nipple and spoke point toward the target flange. Here's another picture showing us the alternating angle of the hole drillings. In the vast majority of rims, these up and down angles are the same, and this is true for both carbon rims as well as aluminum rims. The reason for this is because the rim manufacturer has no way of knowing in advance what kind of a hub the rim is going to be paired up with. The typical angular deviation from the center line is about 6 or 7 degrees. Here's another picture looking at a rim from the inside. The piece of red tape is covering the valve hole. In most cases going clockwise from the valve hole. The first hole will be angling down and the next one angling up, and so on. This is a wheel I'm in the process of rebuilding, so some of the spokes have been taken out, but perhaps you can see that by looking at those 3 rods, all of the holes are drilled straight through, no angle up or down. And I generally try to avoid a rim like this because of the fact that the nipple alignment is not ideal. Some rims are drilled with more specificity. In this case, this is a rim drilled specifically for a rear wheel or possibly a front disc brake wheel if it's turned around. We have a wider angle on the left going to the non-drive side flange and a narrower angle on the right going to the drive side flange. Let's try to make this point a little more clearly, and I will expand this section of the rim so that it looks like that. There is a center line. If I drill my holes straight out, they're going to look like this with no angle. If I look at the angle that my drive side spoke has to make going from the rim to the hub flange, it's clear that I'm better off if the hole that I drill through the rim is the same angle. On the non-drive side of the wheel, my spoke has to take a wider angle, so my hole drilled through the rim should also be a wider angle. In this perfect world, the angles of the holes drilled through the rim are the same as the angle that the spoke has to make to go from the rim to the hub. As I was doing some final editing of this chapter, I stumbled upon this wheel that's even worse than the one I showed you before with a great big motor in it, and I wanted to stick it in at the end of this chapter because this one shows a new problem. This wheel we're looking at from the drive side, you see the freehub body, and this is actually a disc brake wheel. It's a 700C wheel, and we're looking at a hub that has a hole flange diameter of 220 millimeters. It's a 36 spoke wheel. here are just one pair of spokes of the 18 pairs on both sides, and you can see, I hope, that these spokes are nowhere near tangential, so they're in no position to be able to transmit torque either when accelerating or decelerating. Consequently, the wheel has to rotate quite a bit in order for that to happen, for that torque transfer to take place, and the wheel is very, very vulnerable to spoke breakage.